Hello again. Today we're going to talk about free or natural convection. This is the heat transfer due to the motion of a fluid, which resulting from density differences between the fluid and the surroundings. So let's look at a sort of representative situation. Look at a hot vertical wall. Heat transfer into the fluid from the wall will result in a fluid boundary layer moving upward. As the heat goes into the fluid, its density will decrease and it will then rise relative to the surrounding fluid. And what forms is a very thin boundary layer. We give it a thickness delta, and we have a vertical height h, and the wall temperature we'll call T sub s for surface, and then out here at T infinity is the surrounding fluid temperature before the heat comes in. Now notice the velocity profile. It has a maximum some distance off. It's usually about a third of the way up toward the edge of the boundary layer. Zero velocities at the wall and zero velocities at the edge of the boundary layer where there's no temperature difference. And we're going to go ahead and assume that the velocity and the thermal boundary layers are the same. They really have to be, otherwise there wouldn't be any fluid motion. So what are the questions we're going to address in the next few minutes? What's the heat transfer coefficient? What are the governing parameters? What are the laminar and turbulent regimes? And what's the effect of geometry? Flow about a heated cylinder or flow off a hot plate? So the way we're going to address this, the book has a nice, more analytical approach. As you know, I like to use scale analysis and then apply that to the equations. So let's cover up some of this alphabet soup here initially. What are the equations? Continuity, momentum, and energy. We have x going up, y into the boundary layer, u going up, v velocity into the boundary layer here. And our length scales will be the height along the plate and the thickness of the boundary layer. Continuity, you've experienced that in fluid mechanics. X momentum is nothing more than the acceleration equal to the sum of the forces per unit mass. We'll be looking just at viscosity and buoyancy, and I'll define this beta in just a second. And then we also look at energy, since this is a heat transfer class. And then essentially the convection of energy into a small element is equal to the conduction profile across the element. So when we do a scale analysis, we look at a balance of terms. I'll ignore the momentum terms and just look at viscosity balancing with buoyancy. And so we'll just have the viscosity term on the left and the buoyancy term on the right. Now what is beta? That's the coefficient of thermal expansion, and that's equal to minus 1 over the density and the change of density with temperature at constant pressure. If you put the ideal gas law into here, that's just equal to 1 over T. But again, when you do the homework problems, T is always in degrees Kelvin because it's from the ideal gas. So when I go ahead and do the scale analysis of this viscosity buoyancy balance, I have this particular ratio, and that will then let me solve for the vertical velocity as a function of the temperature difference and the boundary layer thickness. When I go ahead and apply scale analysis to the continuity equation, and you can look at the details when you look at these notes, I get an equation for the the horizontal velocity v, which is very, very small relative to the upward velocity. And then when I go to the energy equation, do the same analysis, and then I combine the momentum equation with the energy equation, I get an interesting relationship between the boundary layer thickness, the height scale, and my thermal parameters, thermal diffusivity, viscosity, gravity, coefficient of thermal expansion, temperature difference, and height cubed. So what do we do with that? Well, again, because engineers are lazy, we just say, let's just put these together in a dimensionless form. And we'll call that dimensionless form the Rayleigh number. Rayleigh was an interesting fellow. He was the first to explain why the sky is blue, and that reason is called Rayleigh scattering. And he was also from a wealthy English family with land titles. So his name really is John Strutt, but if you're from the barony of Rayleigh, you're called Lord Rayleigh. And this is all back in the really the late 1800s, early 1900s. So what we could do is just gather these terms, and the Rayleigh number goes as the vertical height to the boundary layer thickness to the fourth. Again, there is conduction across a laminar boundary layer, so you can go ahead and write the heat transfer coefficient as the thermal conductivity over the boundary layer thickness. When you substitute that into the Nusselt number, you end up with Nusselt number is proportional to the Rayleigh to the 1/4. So that's how that comes about. Now, here's where we can simplify things a bit. I got a bit irritated having to look up values for thermal diffusivity and viscosity, and then divide them into gravity and thermal expansion. And actually with water, this is a pain. You have to look that up as well. So I went ahead and did a curve fit. So here are two curve fits you can use for temperature and Kelvin to give you the value of these parameters. So please feel free to use those in the homework problems. And then the temperature at which you evaluate the properties, because we're dealing with a boundary layer, it really is just the film temperature. So the last thing we'll do is go ahead and look at the correlations which we'll use for the homework problems. This has kept people funded for many years measuring these, and I was funded for many years developing correlations for buildings. One thing to consider is not only the geometry, but whether it's laminar or turbulent flow. And interestingly enough, when you go to turbulent flow, the Rayleigh number is proportional to the Nusselt number is proportional to the Rayleigh number to the 1/3. And so when you look at the mathematics, the L's cancel out. And so the heat transfer coefficient is really just a function of the temperature difference. And here's what I use for these various geometries. Vertical plate, Nusselt number, the length scale for the Nusselt and the Rayleigh is the height of the plate. So it's an average value. For horizontal surfaces, you need a length scale, so you'll use the area over the perimeter. And then there's basically two situations: whether or not the plate is being heated or cooled, and whether or not you're looking at above the plate or below the plate. And then finally, for the horizontal cylinders, the length scale is the cylinder diameter, and again, two correlations depending on whether it's laminar or turbulent. One single correlation for a sphere, and the last homework problem is an enclosure, and that there are sort of two equations which I use, depending on whether we're heated from the side, like in a case with the last homework problem, which will be the double pane window, or whether you're heated from the bottom, and then that's a different physical situation. And it turns out there's a critical Rayleigh number for the onset of convection. It has to be greater than 1708. And if that's the case, then here's the correlation. And again, just want to point out that the length scale, when you have an enclosure, is really the distance between the hot and the cold plates. So L is here for side heating, and then L is basically in the vertical dimension for bottom heating. So that should be enough to get you started. Please read the chapter and then do the homework, and I'll talk to you later. Bye.